Hello, good evening. I'd like to continue with this pavement design. So we have talked about the the empirical approach. We have talked about the mechanistic approach. We have talked about the design traffic as well. So this one, this last session, I'm going to talk about some examples. Okay, so the first example will be about the this design of just a spray seal surface with unbound granular pavement. Just granular pavement, just spray seal. There's no structural strength for the spray seal or the chip seal. The second one I'm going to talk about is the it's a asphalt pavement containing cemented material subbase. Okay, so this one will be like three. There are three type of damages. You know, we consider the damage. This one, the stress at the tensile stress at the bottom of the asphalt, tensile stress at the bottom of the cemented material, and the deformation at the top of the subgrade. The first one will be because it's a granular pavement and then just spray seal on top. So the only distress is the deformations at the top of the subgrade. Okay. So I'm not going to go very detailed on these things on the materials part. I'm going to skip some of the material part because we'll instead of doing all those the thing, it will be replaced with the software, the circuit software. So which I'm going to show to you at the end of this session. Okay, so I probably just go through for the material input. I just going to skip through, and then but later I'm going to compare the design traffic as well as the design traffic standard, this one, the ESA, and then the allowable ESA. Okay, for this unbound granular pavement. But for the bound pavement asphalt with the cemented material, I'm going to check the later on at the end. We'll be checking the design standard standard Excel repetitions. Okay, the design standard Excel repetition for the asphalt, for the cemented material, and for the subgrade. Okay, and then we check against the allowable. Okay, see whether it is smaller than the allowable, because it cannot be greater than allowable. If your design standard Excel repetitions of the three types of the distress, if it's greater than the allowable, the distress, the standard Excel these repetitions, then the pavement will fail. Okay, so it's supposed to be less than the allowable. Okay, so we just go through this. The first one, the spray seal surface unbound granular material. So spray seal, the thickness, we just put 0. Okay, we're not going to put anything. And then the unbound granular materials, 475 mm. So this is a trial. We try the pavement composition and the thickness. So okay, the subgrade that is 4 CBR got 5%, and then in mechanistic the design. So we're going to become like 55 times 10 CBR go to 50 MBA, and then the modulus. Okay, I'm not going to go too much detail. Modulus is 0.5. This one for the different material, for the unbound granular materials. So the modulus is this much. Okay, and then the other thing as well, the Poisson ratio as well. So this Poisson ratio is 0.35. I'm not going to go too much detail, and yep. So I just skip this the material. So because I think in the software we just choose certain type of material, and then they'll be listed what are the modulus, what are the Poisson ratio. Then we just select the material, and then all the material characteristic will be input. Okay, so as I said earlier, for these deformations, granular pavement, there's only one type of deformation, which is the permanent deformation, or at the subgrade. So this is the allowable, this one, the repetitions, or the standard axial repetitions. Okay, so this is the formula 9300 divided by microstrand to power 7. Okay, so the NDT is in terms of the this is the HVAG. You know, we remember that previously we talked about the in the design traffic, we talk about the NDT. NDT, this is the is a cumulative heavy axle group, heavy vehicle axle group. The unit is HVAG. Okay. Okay, so the permanent deformation of the subgrade is the controlling distress mode. Okay, so we need to change the HVAG to ESA. So there's a conversion factor, you know, ESA divided by HVAG 0.7. So this is based on actually the actually for the granular pavement, ESA over HVAG for presumptive rural is 0.9, and then for presumptive urban is 0.7. So so I think we be, this is the urban, so I think it's a urban, I think it's an urban road, so it's not, probably it's not mentioned. So we're going to choose the urban okay, 0.7 for urban traffic loading. So ESA over HVAG we're going to choose a 0.7. So using the traffic load distribution on table, I think this one I just skip it. Okay, this one not the bottom one, I think I haven't, I'm upgrading my notes, but this one I'm not going to use the SAR, but I want to compare with the ESA rather than, you know, this one. I think we just tap not after I will delete this one as well. We're not going to use the ESA. So this one, the design ESA, design traffic in terms of ESA, the unit ESA 7 times 10 to the power 6. So this one are these are the steps in the OSROD for the mechanistic design. Okay, so we're not going to look too much. We're going to run the software. Okay, we'll run the software, the Circle 6, and then we'll try to find, you know, you run it, and then there we'll find the max, the damage value, and then the critical strength. In the Circle, later on I will show you, we'll at the end of this session will show you how to run the Circle 6. So in this for this for this example, we're going to run the software, the critical strength, which is the strength we need to change to microstrand. So the strand is 0.90557 to the power of minus 3. So the strand, when you multiply by 1 times 10 to the power 6, it becomes microstrand, 906 microstrand. Okay, so this is the microstrand, you know. So this is the this is the 906 microstrand. Okay, so so the permanent deformations, permanent deformation, based on this formula, so it will be 9300 divided by 906 to the power of 7. Okay, 9300 divided by 906 divided by 7 equal to 1.2 times 10 to the power of 7 SAR 7. This is the this formula will give an expression of the SAR 7. This is allowable standard axial repetition. For the 7 means that is for the subgrade or the permanent deformations. So to change it to the ESA, so we just in this case we just divide by 1.6 because you see the subgrade. I think I can show you this one. SAR 7 divided by ESA equal to 1.6. So to get ESA, so ESA you bring over, and then the bring over, you know, if you cross multiply ESA you bring this one, actually SAR 7 divided by ESA equal to 1.6. so it's a ESA you bring over to the right, and then that will become ESA equal to 1.6 times SAR 7. Is it correct? Yep. Okay, just a minute, I just stop it for a while, pause. Okay, sorry for the stoppage just now. Okay, so let's check. So the from the printout, from when you run the circuit 6, so I find that the critical strand is this much. Okay, the which when we transform it, it become the 906 microstrand. Okay, so we submit in, we just put it into this formula. Then we get where is that? We see so it become this one. So it's equal to 1.2 times 10 to the power 7 SAR 7. The unit for this N is from this formula is actually SAR 7. So it means standard axial repetitions for the permanent deformations or subgrade. And we need to convert to the this one, the the ESA. So to convert it into ESA, you have to divide by 1.6. So I just from this, so the this one for the routine and shape loss, SAR 7 divided by ESA equal to 1.6. Okay, so the ESA will be equal to SAR 7 divided by 1.6. Okay, ESA you bring over that to the right, and then the 1.6 bring over to the bottom, so SA become SAR 7 divided by 1.6. That gives us the ESA. Okay, so that will give us the allowable the the repetitions allowable. So that means is the this is 7.5 times 10 to the power of 6 ESA. Okay, so the allowable loading is 7.5 times 10 to the power 6 ESA in compare with 7 times 10 to the power 6. So this is the design traffic loading is 7 times 10 to the power 6. So it's greater than the allowable is greater than the design, so it's okay. So the trial pavement composition is acceptable. So this is for the first case. For the this one, the chip seal pavement with the granular aggregates. Next, we're going to look at the this asphalt pavement containing the cemented materials subbase. So we try this pavement composition. We try the top two layers. They are the 14 mm asphalt, and then E equal to 2200 MPa, and second layer is 20 mm asphalt, E equal to 2500 MPa. Okay, so and then the third layer is the cemented material, 2000 MPa, and then we try 150 thickness. So the asphalt is about total of 175 thickness. The granular material at the bottom is 200, and on top of the subgrade of CBR5. So it's the thickness of asphalt over the cemented material is greater than or equal to 175. The post-cracking phase of the cemented material life may be considered as the thickness of asphalt over the cemented material is greater than 175. Is greater than or equal to. So this one, the asphalt is 175. So is equal to 175. So the post-cracking phase of the cemented material life may be considered. So this cemented material is 150. So we can, in this case, we can consider the scenario, the cemented material crack, and then there's a pre-cracking. We consider pre-cracking and then the post-cracking. So I think because of this, you could you could if you opt not to consider the cracking, then probably you have to. That means that you want to design that there's no cracking in cemented material, then your thickness probably have to be greater. But if you consider cracking, you allow the cemented material to crack, and then we consider after the post-cracking whether to ensure that the pavement still sound and not fail even though there's cracking, and there's the crack will not reflect up to the asphalt because it's quite thick, it's 175. So that one probably we can consider, probably we can save some thicknesses for this pavement. Okay, so this we consider in this example we consider the pre-cracking of this cemented material, and also later on we consider the post-cracking of the cemented materials. It will give different value. We can consider the strength later on, and make sure that this satisfy the design traffic loading will not exceed the allowable this one, the standard axle repetitions. Okay, so the CBR 5% become 50 MPa. So we consider subgrade, and then we consider the granular layer. We have to input all the granular layer as well, the modulus, and then the Poisson ratio, and then we're not going to look into too much detail on this. How to it's quite complicated, because we're going to use exactly 6 software anyway. So the cemented material, we enter all the this one, the modulus and the Poisson ratio, and asphalt as well. Asphalt we're going to we choose the for this 14 mm and 20 mm asphalt. Enter the value. So the three formula that going to be used to find the allowable standard axle repetitions. This is because there are three types of distress. One is for the permanent deformation or the subgrade deformations. So this one to the power of 7. And cemented materials is this expression to the power of 12. And yeah, we're going to consider the reliability factor equal to 0.5. And the asphalt is this expression to the power of 5. So in this case, we're going to assume the volume of bitumen of VP is equal to 11% of bitumen, and the reliability factor equal to 0.67. Okay. So this is a formula that we're going to use. We know all these things, know the value here, E, and then except for this micro strand, this mu micro strand here, the 3 micro strand. This one we need to get it from the circuit's output. Okay, so we need to run it. We input all the materials, input all the strand characteristic. We put into the software, run it, and the printout will show us the critical strand. So this one, the micro strand, we'll get it. From here. This is the critical strand. So you see, you can see that the one highlight, the underline, the black. So this one is the asphalt. The asphalt, the Oxford 2004 example 3 size 20. So this is the critical strand. The underlying one to power, we have to multiply by 1 times 10 to the power 6. And this one is a cemented material. Okay, so we just consider the bottom one because this one, the bottom, because this one, the asphalt, there are 2 layers. We just consider the bottom layers, and the cemented material, we consider the cemented material give us this critical strand. So we need to multiply by 1 times 10 power 6 to get the micro strand. And for the subgrade, these are deformations. So this value we need to multiply by 10 to the power 6 as well. And this is a pre-cracking cemented material and post-cracking cemented material as well. So we got another value for this one, the asphalt. We got another critical strand which is different from the other one. Okay, so that means that all this, the post-cracking, they must satisfy the that means the design traffic loading should not exceed the allowable loading. So so for this one, later on you see that the cemented material, because when it's cracked, the design loading, this one, the allowable standard axle repetition, it become less than the design. It will be less than the design traffic loading, so it fails. But after that, after post cracking, you can check the cemented material again. So actually no, sorry. After it's cracked, you only check the after you crack the cemented material, it become sort of called a stabilized material, and it's the same category as the granular pavement. So we don't consider that. We assume that the failure only happens at the subgrade. So previously, during the pre-cracking, we considered 3 distress. 3. So that means that there's a asphalt and then cemented material in the subgrade. But after cracking, we only consider the asphalt and subgrade. Okay, so based on this three, these are the three formula that we need to input. We need to get the microstrand, and then we put in. We'll do the first. First, we'll do the pre-cracking, and then later on we do the post-cracking. Okay. Okay. Before that, the design loading, NDT got 0.7. I think it's given in the beginning. At the beginning, so the I think it's the same example as the first one. Let me see. So this one is the yeah, this one. Actually, the NDT is 10 to the power 7. Okay. So this is a traffic loading, but we're going to use the CBR 5%. Firstly, we're going to just use the the seal, just a chip seal, and then the unbound granular pavement. But later on, the second case, we're going to use the asphalt 175 total thickness for the asphalt, and then the cemented material, granular materials, and then the CBR at the bottom, which is the subgrade. So so the design traffic is equal to 10 to the power 7 HVAG. HVAG, we need to convert to the this one, the DSA. So sorry, you multiply by the this one, the ESA divided by HVAG, multiplied by NDT. Just now we talked about that. We see that ESA divided by HVAG for the presumptive urban area is 0.7. So 0.7 times 10 to the power 7. So that gives us 7 times 10 to the power 6 ESA. So this is the design traffic. Because later on we need to check the different layers and the different response from the asphalt, different response from cemented material, and different response from subgrade. So we need to find the design standard Excel repetition, the design standard Excel repetition from which we change from the ESA to the various. So to change the ESA to DSA, DSAR 5, DSAR 7, DSAR 12, we just multiply by the factor here. 1.1, 1.6, 12. For the asphalt, we multiply by 1.1. This one, the 7 is subgrade, we multiply by 1.6, and for the cemented material, divide by multiply by 12. So you can see that this is for the asphalt, we multiply by 1.1. SAR 5, when you put this ESA over, it becomes SAR 5 is equal to 1.1 multiplied by ESA. And for SAR 7 is 1.6 multiplied by ESA, and SAR 12 is 12 multiplied by ESA. Okay. So that we get the corresponding SAR value from the ESA. So we got this value: 7.7 times 10 to the power 6, 11.2 times 10 to the power 6, 84 times 10 to the power 6. Okay, so these three values. Later on, we need to compare the allowable SAR, standard Excel repetition, for the various layers. Okay, we just proceed. From the first, we find the pre-cracking cemented material. So pre-cracking, we have 47, 134. For the asphalt, it's 47 microstrand, and for cemented material, it's 134 microstrand, and subgrade is 290 microstrand, which is from here. This is for this value, 0.47 times 10 to the power 4 multiplied by 1 times 10 to the power 6, that give us 47. And this one 0.13 times 10 to the power 3 minus 3, that will it will give us I think it's the 134. 134. And this one 0.29 times 10 to the power minus 3 multiplied by 10 to the power 6, it will give us 29 where is that, 290. So these are the value which we can put into this for the various, for the micro strand, we can put under these three formula. So these are the steps. Okay, so we just continue. So we check for the the cemented materials first. So this expression, we put in the 134. Where is it? 134. Cemented material is 134. So I put in. It gives us this SAR value, 8.21 times 10 power 5 SAR 12, and less than, which is less than, this one is less than this value, isn't it? Because this one is the 84 times 10 to the power 6. It's a design 84 times 10 to the power 6. The 12, this is cemented material. This is the design. So the design is greater than the allowable. It's not good. So that means it's failed. It failed. That's why it is not good. It failed. That's why there's cracking. That's because it fails. This cemented material fail, and of course it will crack. But later on, after it fails, it become a granular material, granular pavement, or stabilized material. Then after it cracked, then actually we don't consider as for the tensile stress again. So we don't consider that. So we, after cracking, then the post cracking, we only consider the asphalt tensile stress as well as the deformation at the subgrade. So this one's pre-cracking is did not pass. The permanent deformation of subgrade. So I put in the 19300 divided by 290, okay, for the subgrade. That gives us 3.49 times 10 to the power 10 SAR, which is greater than 11.2 times 10 to the power 6. 11.2 times 10 to the power 6. 7 it represent the deformations. Okay, so it's greater than the design. The allowable greater than design is okay. And the asphalt is 4.51 times 10 to the power 9, greater than 7.7 times 10 to the power 6, which is 7.7 times 10 to the power 6. DSR 5, this is asphalt. So this is okay. Also the pre-cracking phase, only the cemented material is not good, it fails. So after that we have the post cracking. We post cracking. So they give us the software you run. Actually it gives the value at the same time. It will, there's no second. It will just automatically they run the when you specify, it will run the pre-cracking and post cracking the informations. So the post cracking, this is a formula here, okay, that we actually is inside the guide, the Oxford guide to the pavement technology in part 2. So actually there's a formula there. So this one it come out to be, actually the result give us this ESA. I convert to the SAR 7. So ESA convert to SAR 7, you have to multiply by the value 1.6. So for the deformation, you remember is the factor is 1.6. Just going. So for the routine and shape loss, which is deformation, the factor is 1.6. So ESA SAR7, if you change to SAR7, SAR7 is equal to 1.6 times ESA. Okay, SAR7, this one, the ESA go to the right hand side, become 1 times 6 times ESA. Okay, so multiplied by that, so become 1.92 times 10 to the power 9 SAR7. Okay, this is for the permanent deformations. And for the fatigue, the asphalt fatigue, this is another formula. So it gave us the 7.1 times 10 to the power 6 ESA. For the asphalt is multiplied by 1.1. Okay, 7.1 multiplied by 1.1. The fatigue of the asphalt, so SAR5 divided by ESA is 1.1. Okay, so we just multiply by 1.1. 7.1 times 10 to the power 6 multiplied by 1.1 comes 7.81 times 10 to the power 6. So the next step is that we check the permanent deformations. This is allowable, and this is allowable. The first one is allowable, 1.92. This is 1.92. It's greater than 11.2. This is a design standard axle repetitions times 10 to the power 6. So allowable greater than design is okay. Allowable greater than design. Okay, 7.81 times 10 to the power 6 greater than 7.7 times 10 to the power 6. Okay. So for this shows that the distress is satisfied. So the trial pavement composition is acceptable. So this we started with this trial composition. The various type of material that we use, the strength and the Poisson ratio and the thicknesses. And then we find that it's okay. The check-in, what is check-in? The thickness, all these are the allowable SAR is greater than the design SAR. Okay, so it's okay. So now I want to show you how to run the circuit software. So okay, that's all for the I think the PowerPoint notes. So I just go to run the this one. For this is how to run the circuit software. Okay, so this one we're going to use it for the project 2 as well.
Hello, good afternoon. I'd like to show you how to run the circuit software. Okay. So we want to create a project. We go for a new one. Let's say I just do a project 2. And I create layers. I want to start a new project. This just now I've done project 1, so I'm going to do a project 2. So the ID, for example, I just if you have your student ID, you just put in your student ID. For my ID, I just put it 1, 2, 3. And this one I put project 2. Okay, so for this trial pavement, I'm going to use two layers of pavement, 2 layers of asphalt, and on top of the cement layers of cemented materials, and followed by these granular layers, and all this on top of the subgrade. So the first layers I'm going to use is size 14. And with this one, the modulus of 2200. Second layer they're going to use is a size 20 Osrod 2004 with a E of 2500. The third layer I'm going to use is the cement stabilized. Okay, so the modulus, the one with the I'm going to use is the one with the modulus of 2000. The next layers I'm going to use is um, the unbound granular Oxford 2004 and modulus that the one going to use modulus with modulus 200. And all these four layers they'll be sitting on top of a subgrade. So I'm going to use subgrade to Oxford 2004. Okay, so with the material properties specified, I'm going to put the thicknesses for each of the layers. For the first layers, the size 14, I'm going to put 60. And for the size 20 asphalt, I'm going to put 115. So they make up 175 total thickness. And the cemented layers, I'm going to put thickness of 175. And for the granular layers, I'm going to put 150. And for the subgrade is we can't measure there's no thickness, so we let it be 0. But subgrade the subgrade that I'm going to use is CPR with CPR 5. Okay, so we have done the properties and the thicknesses, and we need to put in some input data for the this one, the design traffic, the design ESA. So the design traffic that we're going to use is 20 million ESA, which is 2 times 10 to the power of 7, 2E7. And for the traffic multipliers, we're going to use the Oxford, the Guide to Pavement Technology Part 2, Pavement Structure Design. This is the presumptive traffic load distributions factors. So for the asphalt is 1.1, for the routine and shape loss, which is a subgrade, which is 1.6, and for cemented material is 12. So if you got any other data, for example, the WIM data or the data selected from the WIM data, you could use them. So I'm going to use the asphalt values 1.1, and for the cemented material is 12. And for the subgrade is 1.2. And I'm going to run it by clicking this analyze. So from the output for the various layers, the asphalt, the two asphalt layers are okay, and the granular there's no value, there's no damage factor, and for the subgrade is okay. So only the cemented layers, the cumulative cumulative damage factor is more than 1. In this case, is 60. So the CDF actually is the actual repetitions over the allowable repetitions. So we need to, the acceptable value should be less than 1. So what we can do now is that we could change the materials, different type of modulus, or we can change the thicknesses. So we go back to layers. I want to change some of the materials properties, which is I want to improve the properties. So for the cement materials, I'm going to use 5,000 MPa instead of the 2,000. And for the subgrade, and for the granular material, I'm going to improve it from 200 to 300. And for the subgrade, I'm going to use 8% CPR instead of the 5% CPR. Okay, so I've altered the material properties and improved the properties, and I analyze it again. And we can see that now the cumulative damage factor has reduced to 2.4 for the cemented material. So we still need to do some changes to so that this one is below 1. So I'm going to go back to layers. I'm going to change the thickness of the cemented material. I change it from 175 to 200, and I'm going to run it again. So now it is okay. So we can see that in this case, all the layers are below 1. So with the cemented material is 0.6. So if we look at the print, we can see that the damage under they have this job summary file, they have the damage file and the CLO file. So look at the damage file. We can look under the damage factor. We can see that for the value for the different things, okay, for the cemented materials and for the subgrade materials and the updates the asphalt materials. So the critical one actually is the cemented material is 0.6. Okay, the rest is much less than 1. So I hope this video will help you to know how to operate this circuit software. Okay, by inputting the different the different layers, the materials, and the thickness. If you need to change the properties, then actually we can put some new properties in it as well. So besides that, we also learn how to do the input the design traffic and the traffic multipliers as well. So hopefully you can use it to understand more about the design of the mechanistic of design of the multi-layers pavement by the mechanistic approach. In this case, we use the circuit software to run it. So thank you very much for listening.
Okay, yeah. I just realized that just now the circuit software that was done in 2016. The traffic multiplier, I just saw that there are three multipliers. So I just put it's supposed to be 1.1, 1.6, 1.2 for the asphalt is 1.1 is correct, and then the cemented material is 12 is correct, but the rutting and shape loss supposed to be 1.6. I think in that circuit software I put instead of 1.6 I put 1.2, so that was a mistake. Okay, so please be aware when you do that run the software that the deformations, the permanent deformations, it is called sometimes the rutting and shape loss permanent, or it called the permanent deformation, or sometimes the subgrade distress. It should be 1.6 and not 1.2, which was I think that one was mistakenly put in as the multiplier for the permanent deformations. Okay. Yeah, so I think that's all for this pavement design of flexible pavement. So there are 4 parts, so this is the last part. So thank you very much. I hope this will be helpful. Thank you.